Section 3.5 is composed entirely of word problems. So we'll try to go over these in great detail. Be sure and email me if you have any question about anything that I go over. You'll notice that they begin this section as we began our definition of the derivative by talking about average and instantaneous velocity. They're going to go over this same concept at first. Let's look and see what we have here. We have this graph. The black line here represents how the particle or whatever it is that's moving, the object, is moving with time. So S represents the distance, and this distance is increasing with time. Notice how that the distance is increasing quite a bit in just a short amount of time here. We would say that this velocity of this object is quite large compared to the velocity over here, where the distance is not increasing too much with time. So I'm able to look at what the velocity is doing by looking basically at the slope of either a tangent line or a secant line. And we begin our talk, our main goal is to talk about the tangent line, but we begin by talking about a secant line because we've looked at slope for many years now. If I look at the slope between any 2 points, that'll give me the average velocity between those 2 points. If I make those 2 points closer and closer together, that gets closer to this tangent line. Notice that if Q were, say, right here, then that secant line would look like this, and that would be much closer to the this average value of velocity here would be much closer to the instantaneous velocity of this red line, which is what they're trying to show you here. So this secant line gives me the average velocities, and the tangent is going to give me that instantaneous velocity. And they don't spell it out here, but let's just go ahead and say the slope of the secant line is just that change in y over change in x. And if I were to write it out formally, it would be some sort of f of, in our case, a plus t, or delta t, minus that f of a all over, that would be a plus delta t minus a, which would end up giving me delta t. So the slope of the secant line, which is right here, it is right here, slope of the secant line, could have just written it here, is very closely related to the slope of the tangent line. All I need is to make those 2 points so close together that their distance becomes 0. And that's the main difference between the secant and tangent lines. Alright, trying to figure out what they've got going here. It looks like we have a police station, and then we have a roadway that travels east or west, and we're going to consider this police station to be at point 0, and that distance, that S value, is going to be positive if I'm traveling east and negative if I'm traveling west. They ask me, they give me a graph, and then they ask me to talk about where the police car is, where the patrol car is during the first 3.5 hours of the trip. So I see that the car takes off, and he doesn't automatically take off at he takes off slowly, and then he increases in speed. He goes looks like he's going a steady speed here because that slope is not changing. Then it seems to me like it slows down. The slope here is 0, meaning that his distance isn't changing, his position isn't changing, so he stopped. From about 1.5 hours to 2 hours, he must be sitting there eating lunch or something. Then he takes off again. He doesn't just slam the pedal down. Notice how he takes off at a reasonable rate and starts to increase in speed, and then he goes at a steady speed. So let's talk about where he is. He's going to be going east because his position is positive. So he goes east until it's about, I don't know, 1.5 hours into his trip. So he goes east for 1.5 hours. Then he stops. He stops for a good half hour. Then he travels back, and he gets a little on the other side of the police station. He gets about 20 miles. Yep, it's in miles. So he gets about 20 miles on the other side of the police station, and he got 80 miles east, and then he travels and gets 20 miles west. So that's describing the location and what he's doing. That's A. Calculate the average velocity between noon and 2 p.m. So between noon, let's see, this car takes off at t equals 0 is noon. So this is, oh, well, that's nice. This is, if this is noon, that's 1 o'clock, 2 o'clock. Cool. So calculate the average between noon and 2. So I need to know the average velocity. Average velocity is just plain slope. So for B, I'm going to do average velocity equals f of 2 minus f of 0 all over 2 minus 0. I'm just doing the change in y over the change in x. F of 2 is 80 minus, at noon, he's right there at the police station, over 2. So this is going to be 40 miles per hour. That's for the B part. The C part. Calculate the displacement and the average velocity of the car between 2 and 330. Between 2 and 330. So here's 330. The displacement, I can see, it just means what's the distance between these two dots. And that's going to be, it's 80 to here and then another 20. So the displacement is 100 miles. It's how far away are the two dots on the Y. Then the average velocity is going to be f of 3.5 minus f of 2 all over 3.5 minus 2. Just getting those values, negative 20 minus the 80 over, just got the y value here and the y value there, and this is going to be over 1.5. And when you crunch those numbers, you're going to get approximately negative 66 point and rounding 7 miles per hour. All right. At what time is the instantaneous velocity the greatest as the car travels east? I believe that to be in between here and right about somewhere in here where he starts to slow down a little bit. So I'm just going to say, from looking at the graph, somewhere in between 0.5 and 1 hour, or that would be 12:30 to 1 o'clock if they want the exact time. So I'll say 12:30 to 1 o'clock p.m. E. At what time is the patrol car at rest? It's totally stopped. Looks like about right here and right here. So I'm going to say it's totally stopped in between 1.5 and 2. So that would be 1:30 p.m. to 2 p.m. Finishing up on this idea of position and velocity, we're going to move on to acceleration. And acceleration is how an object, how his velocity or how his speed is changing with time. So velocity happened to be how the position was changing at time. So if I had velocity is position changing with time, and the velocity happens to equal the derivative of the position. Acceleration is velocity changing with time. So how is that speed changing with time? So similarly, I would say that acceleration is the derivative of velocity, or you could even say that it's just the second derivative of position. And that's what they're giving you in this definition here. They're just explaining that acceleration is the derivative of velocity or the second derivative of position. And then speed doesn't take into account direction. Notice in that other problem we were talking about east is positive and west is negative. Speed would negate that direction. So let's see what we're looking at here. We're given some sort of object and it's moving horizontally, and here is the function that it's moving from 0 to 5 seconds. Okay, good, seconds. And what's happening is that this position has a negative value, so this object is moving in this direction away, or you might say west, as was our other problem. And this object is moving in a parabolic motion. The A question asks me to graph the velocity and determine when the object is stationary, moving to the left, moving to the right. Velocity happens to be the slope of the tangent line at any point along the curve. Let's look at what the tangent line is doing as we go along this particular function. I notice that the velocity is slowing down here. It's slowing down, and then the slope here of this tangent line is 0. So the object actually stops right here, and then the velocity is going the other direction, is going in a positive direction, and it is increasing in speed. Notice how the slope is increasing. Let's look at what that does. Get a different color here. Get a red. The velocity is the derivative of this position function. The velocity would be 2t minus 5. If I were to graph that, let's see, I'd have this 5 here, and it would have a slope of 2, so that is 2 over 1 up 2 over 1 up 2 over 1, and so forth. Here is my v of t function. So I graphed it, determining when it is stationary, moving to the left and moving to the right. Okay, it is if moving to the left is negative, which usually they're describing it as such, I would say that it is moving to the left from time equals 0 to, imagine that's 2.5 seconds. We'll get that in just a minute. From 0 to 2.5 seconds. And then it's moving to the right because the position here, it's negative and becoming more negative, and the position is becoming going towards the positive direction here. So I would say that it is moving to the right there. Then we'll say that it is moving to the right because that position is going towards the positive. So that's between 2.5 and 5. I keep putting that thing on there. Let me get that off of there. It's not right at there. Alright, so how would I know where the velocity is 0? Well, I have the function there. So what I can do in order to see where that velocity is 0 is I'll just say, where is v of t equal to 0? 2t minus 5. Solve for t, and I'll get 2t equals 5. So at t equal 5 halves seconds is where the velocity is 0, which we already knew by looking at the graph. It's very symmetric. Graph the acceleration function. Right, the acceleration function is the derivative of the velocity. So I'm going to take the derivative of the velocity, and that would be 2. The acceleration is a constant. The velocity is changing, but the acceleration is a constant. So it's determine the acceleration of the velocity, acceleration of the object when the velocity is 0. I don't care what the velocity is. The acceleration is always 2. They give me any sort of, this would be in feet per second squared, and this would, and then your velocity is in feet per second. Describe the motion of the object. Okay, well, I think we kind of did see first, but the object is moving, we'll say west, or some direction we're calling negative, and it is slowing down, and as it gets to the time period 2.5 seconds, then it stops, changes direction, and then speeds up again. And I think that does it for this one. We're going to talk about freefall now. Just as a side note, I did want to mention that gravity in our SI system is 9.8 meters per second squared, and if we're using feet, then you'll notice the 32 feet per second squared value. Those of you that have had physics might know that the position function is -1/2 AT squared, or -1/2 times gravity squared, and that is why this is a 16 here because a half of 32 is 16. So if I was looking in these metric units, this number here would be half of the 9.8 would be 4.9. All right, that's just a side note. So I have thrown this stone straight up, and I've got a bridge above a river. So got a bridge. Here's the water going through. Here's my bridge. Tink, 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 tink. See my little handrail. So somebody is up there and they threw a stone straight up. Let's just throw it off this side, and it goes straight up and straight down into the river. And that's what's going on here. Lovely little picture. My picture was going to get in the way. I got him out of there. Find the velocity and acceleration function. The velocity is the derivative of the position. So the velocity would be negative 32t plus 64, taking that derivative. The acceleration function, take the derivative of velocity, negative 32. Done with that. What is the highest point above the river reached by the stone? I graphed it. You can see that they graphed it. I'm going to look at my graph first, because this is what you're going to be doing when you have one of these problems, is you're going to have to graph it and look at it. So I graphed the function negative 16. You can see I'm sitting here, negative 16 x squared plus 64x. I graphed that and adjusted my window so that it would be pretty here. Notice that this is before time. So this part here is meaningless. You can get answers, and algebraically you'll get answers from that, but that stuff is meaningless. So if you get some sort of negative time answer, don't pay attention to it. The meaningful stuff happens here. Also note that this is if it were to continue underwater at that same rate, which it's not going to do. This is where it strikes the water. So this is the water part. They want the highest point above the river. The highest point above the river would be where the velocity is 0. That's one way to do it. So let's do B. The velocity here at the highest point would be 0 and negative 32t plus 64. And solving that for t, I would get that t happens to be 2. So at 2 seconds, it's going to be at its highest point. Let me see if that looks good on my graph. Yeah, it does. That looks like the highest point. So now I need to know what is that highest point. So I need to know the position at 2. I'll just chunk all of those, this 2 into that equation. Plus 96. And if you crunch those numbers, you will get 160 feet. You could also have used the vertex formula that you learned in your algebra classes, and you could have gotten it that way as well. But we're in calculus, so we're going to use some calculus stuff here. With what velocity will the stone strike the river? Well, I need to know what's that time right there. You could use the quadratic formula if you wanted to, and that's what they go through in their little, I don't know, their stuff in their section that their little content that they go over. I probably would have just used my calculator, so I'm going to show you how to do that. I want to know that value right there on my graph, so I would hit my shift button on my calculator. Mine, it happens to be blue, so I would hit that blue, and then the calculate button, which is right underneath my graph. It is the fourth one over. So I'd hit blue, calculate, and then I'm going to tell it, I want you to find the 0 for me. So you'll notice, here's my next screenshot where I told it to find the 0. With the Casios, it will go ahead and find the zeros directly for you. The TI calculators are a little more cumbersome. It will ask you for a left bound. So I use you use your arrow keys to make this little dude on the left side of that zero. See, here's the zero. So I want to be on the left side of that zero. So I get kind of close to it, and then I'll push enter. And then the calculator will ask me for the right bound. So I've got to use my arrow keys to move that little, I call it my little flower, little spider guy, move it over to the other side of that zero. Here's the zero, and I want to be on the right side of that zero. Once I get on the right side, I hit enter. And then the calculator is going to want you to guess. So you can move that little flower, move that little spider guy, move it somewhere next to the zero. Just be sure that your left bound is on the left side and your right bound is on the right side, and it's going to find that middle ground and where it crosses that axis. That's what it's going to do. And then it will give you the approximate value for that. And if you use the quadratic formula, you would get something pretty darn close to this. So now I have the time when it hits the water. So this is t equal 5.162 is time when object hit water. But they don't want just the time when it hit the water, they want the velocity when it hit the water. So I need to find velocity when it hit the water, and then I just plug that into that formula and then crunch those values, and that would be, so oops, getting my thing, negative 32 times the 5.162 plus 64, and you should get negative 101.1. This was in feet per second, I believe. Okay, and I'll finish the rest of this section in the next video, so this will be the A part.